All right, so I think we can get started. So, questions on ionic, covalent, and metallic bonding. So here we've got a table. So it's just a really good summary of everything. So up here, we got our first row, that's for ionic bonding. Here, our next two rows are for covalent. And our third row is for metallic bonding. Sorry, our fourth row. Most questions you'll get are going to be on the top two, ionic and covalent. So this is the type of structure you can have, the type of compound. So ionic compounds look like this. Within covalent compounds, there's two different types of compounds you can get: simple molecular and giant covalent. Anyone know examples of giant covalent? Do you guys know what the structure is here? You guys seen this? Can I make it bigger? Yes, I'll zoom into just this section. Does anyone know what this is? Diamond, exactly. It's diamond. It can also be silicon as well. So keep that in mind. It can be silicon or diamond. Okay, so we're going to look at the differences in all of this. And then we've got metallic bonding, which doesn't get asked as much because there's not much to know about it. It's just ions in this structure surrounded by a sea of delocalized electrons. Okay, so let's get into the questions. First question is on covalent bonding. So here we've got something called silane. So bonding in silane is similar to bonding in methane. So earlier this week we posted a video on all the covalent compounds that you need to know. Methane is one of them. If you know what methane looks like, it's quite straightforward what the answer to this is. So if you don't know what methane is, the way to work it out is basically look at each of the atoms involved. So we've got one, this is silicon, and we've got 4 hydrogens. Let's note down how many electrons in each of these outer shells. So hydrogen, how many electrons on the outer shell of hydrogen? Can anyone tell me? Hydrogen is the first. Keep that in mind. Yep, 1. Thanks, Simran. So 1. So all of these have 1. So remember what we're going to draw is a diagram. So remember what we're going to do, just the outer electrons. So for hydrogen, let's choose a dot. It doesn't matter which one you choose, but let's say each hydrogen has 1 dot available. Silicon is in, if you look in the periodic table, I don't have one on me right now, you'll find it in group 4, which tells us how many electrons are there in the outer shell. Exactly, 4. So we're going to use 4 crosses for silicon, okay? This is all we can have in this diagram. We can't add any extra dots or any extra crosses, and we can't get rid of any. All of these are going to have to be arranged to give each atom a full outer shell, okay? So if silicon has 4 electrons on its outer shell, how much does it need for a full outer shell? Full outer shell is 8. So how much would it need for a full outer shell? Thanks, Macy. So it would need 4 more. So needs 4. Same with the hydrogens. So hydrogens on the first shell. So remember the electron configurations go 2, 8, 8. Hydrogen's in the first shell. So how many does hydrogen need for full outer shell? 1, exactly. So each of these just need 1. Okay, so what we're going to do is we're going to put whatever an atom needs into the shared part of the covalent bond. Okay, so if we start with hydrogen, let's start with this hydrogen here. Let's say this hydrogen is this one. It needs 1. So it needs 1 to become stable. So what you're going to do, whatever it needs, you're going to borrow it from what it's bonded to. So this one, this hydrogen, is bonded to silicon. So it's going to take one of these crosses from silicon and it's going to share it. It's going to come in the shared part. We can do that with this hydrogen as well. So let's say this hydrogen is that. It's going to share one of the ones from silicon here. And we can do the same for this and for this. So what we've actually done is we've used up all 4 crosses here. So now we need to look at silicon. We need to give silicon a full outer shell. How many does silicon need? It needs 4 electrons. Where is the silicon going to get 4 electrons from? 1, 2, 3, 4 electrons. It's going to get 1 each from each hydrogen. So each hydrogen, so this one is going to give its electron to silicon to share. This one's going to give 1 as well. And all of them, I'm going to give them electrons. And now just to check, we just need to check that each one have a full outer shell. Hydrogen has 2, this hydrogen has 2, this hydrogen has 2. Don't know what just happened there. Okay, let me just redraw that. Sorry about that. Oh, it's back. This hydrogen has 2. Ooh, everything's just moved around. Okay, that's a bit better. So yeah, this hydrogen has 2. This one has 2. This one has 2. And then if you look at silicon, it's got 1, 2, 3, 4, 5, 6, 7, 8. So that's full as well. So all of them now are happy. They're all stable. So that's just a dot and cross diagram. Let's look at this question. 3 marks. Explain why silane has a low boiling point. So the first thing to do is to recognize, so it's asking about low boiling point. In this table here that we have, which row do you think it fits under? Which row do you guys think silane fits under? These questions are higher questions, Simran. Yes, they are. Ionic? No, not quite ionic. Covalent? Yes, it comes under covalent. Now we have to figure out which one of the covalents does it come under. Is it simple molecular or giant covalent? Molecular covalent, Carmel. Yep, thanks. Molecular covalent. So how do we figure this out? Okay, so ionic. Anything ionic is always a metal and non-metal. Remember that. So you look at the silane, we have silicon and we have hydrogen. So if you look in the periodic table, you'll realize both are non-metals. So it's not a metal and a non-metal. It's going to be covalent. That is non-metal and non-metal. Then we have metallic. Obviously it's metallic, so it's just going to be metal and metal. So that's how to tell which one's which. So within covalent, is it simple? Is it giant? What you need to remember is pretty much everything is simple molecular unless it's silicon, diamond, or graphite slash graphene. That's another one you come across. Okay. These are pretty much the only giant covalent ones you come across. Actually, no, there's a few more. So there's graphite, graphene, diamond, silicon. You also come across fullerenes, which are the spheres, and nanotubes. Yeah, exactly, fullerenes. So those are all examples. Okay, so don't worry if you're confused. I'm hoping when we get down to the questions, it'll make more sense. Let's go back to the questions. So Explain why silane has a low boiling point. Like I said, the first thing to figure out is which one does it fall under. We figured out it comes under simple molecular. Okay, so that's because it's a non-metal and a non-metal. Now, why do simple molecular structures have low melting and boiling point? We've got that here. Reason why? Weak intermolecular forces. Thank you. We've got weak intermolecular forces between the molecules. And when you have weak forces, that means you don't need a lot of energy to break the bonds. So where do we get our 3 marks from? So 1 mark is just to identify that it's a simple molecular substance. Next mark is to mention that it has weak intermolecular forces. And the final mark is to mention a low amount of energy is needed to break the forces. Thanks, Macy. Yeah, that's exactly what you need to say. What exam board is this? This question is AQA. I just want to, 1 second. There's a poll I just want to ask you guys. You might see a poll on your screen. If there is, it's just asking what exam board everyone is. I just want to find out what mostly people are doing. So could you just answer it on the poll if it comes up? If not, don't worry about it. This comes under combined. Yes, this is the questions itself is higher, but it comes under combined and triple. And you need to know this for foundation as well. Okay, so does anyone have any questions about this? No? What do I think will pop up this summer? Not sure, but bonding almost likely, very likely to come up yet. I would say this stuff will probably very likely come up. Okay, so let's move on to the next one. Silane reacts with oxygen to form silicon dioxide. Has a high melting point. Right, so we've seen this already. Silicon dioxide. What type of substance is silicon dioxide? That's the first thing to work out. Giant covalent. Thank you. Again, not ionic, because for it to be ionic, it needs to be a metal and a non-metal. Silicon is a non-metal. Oxygen is a non-metal. So that means it has to be a covalent. And we've got here that giant covalent examples are silicon or diamond. So we've got silicon dioxide here. So our answer is going to be all about giant covalent structures. Any questions? What do you guys think the 3 marks will be then? We've got 3 points to mention. It says you should describe the structure, we've just mentioned it, and the bonding. Right, so I'm getting strong intermolecular forces, strong covalent bond. Okay, so I'd say Carmel's right there. Strong covalent bonds. Not intermolecular. Okay, so let me tell you guys a few things. So these, you're going to come across a few bonds. We've got ionic bonds. These are strong. We've got covalent bonds. These are strong. We have intermolecular forces. These are weak. These are the only weak ones that we come across. And we have metallic bonds. Which are strong. Okay, so remember that. Intermolecular forces comes under this second row here, okay? So remember, we got 4 rows. Whenever you get a question, try and think, first thing, which row does this come under? Okay, it comes under the second row here, simple molecular for intermolecular. Ionic comes on the top, on the first row. Covalent bonds would be in giant covalent. So back to this question. Silicon dioxide, explain why it has a high melting point. It's all to do with the giant covalent. So silicon, we've got an explanation here. There are strong covalent bonds which require a lot of energy to overcome. Okay, so what I'll do, once we finish this live, I'll give you guys a chance to screenshot all of this, so it can help you with the revision, hopefully. So what you can say is, first of all, it's a giant covalent structure. Giant covalent structure, and then you need to talk about the bonds within the giant covalent structure. So they're strong. Remember I said covalent bonds are strong. Strong covalent bonds. And what you always need to mention in questions like this about melting point are things about energy. A lot of things of energy is required. Okay, so next question. Here we go. The structure of diamond and graphite. Graphite is a good conductor of electricity. Diamond is not a good conductor of electricity. So it's not on melting and boiling point this time. It's about conducting electricity. What do you need to talk about here if you're talking about conducting electricity? Can you write bullet points, or do you have to write full sentences? I would say you can write bullet points, but just make sure each bullet point is a full sentence, or it's not just single words. It flows. You are allowed to write bullet points in your answers. Can I make the screen a bit bigger? Yes, I can. This is the question. Yep, good. It has delocalized electrons. Perfect. Okay, so whenever it comes to questions about conducting electricity, you need to talk about one of two things. You need to talk about moving ions, or free moving ions. Let's write free moving ions, or delocalized electrons. Okay, so this is about graphite. This is about diamond. Diamond does not have any delocalized electrons or moving ions. It has no moving charges. For something to conduct electricity, there have to be free moving charges. So if we go back to our notes, we've got here, diamond has no moving charges, so there's no free electrons or free ions. Graphite, it does have delocalized electrons. That's why it does conduct electricity. So we can say has no free moving charges. You can say charges, or you can say electrons/ions. Now for graphite, it has delocalized electrons that can carry a charge. So for it to conduct electricity, it needs to be able to carry a charge. So just to recap, if you get any question about conducting electricity, you have to talk about free moving ions or delocalized electrons. So let me add it to here. So if it's, remember the four things that we're looking at ionic, we're looking at simple molecular, we're looking at giant covalent, and we're looking at metallic. So out of these, which ones conduct electricity? Metallic conducts. Simple molecular doesn't conduct. Giant covalent, only graphite, so diamond or silicon dioxide doesn't, only graphite. And then for ionic, it conducts sometimes. Does anyone know when ionic compounds conduct? They don't always conduct electricity, they only conduct electricity at some times. Ionic conducts electricity when it's molten. Good. When molten or something else. It can either be molten or aqueous. Yes, so molten means it's melted to liquid, and aqueous means it's dissolved in water. So only when molten or aqueous. Okay, we'll come back to that later. So we've added that on now. Next question, look at some of this information about ethanol. So we've got the melting point of ethanol, we've got the boiling point of ethanol. Predict the state at 25 degrees. So that's room temperature. What do you guys think? Will this be a long video? Probably not. Probably finish in 8:45 or 9. So some answers saying liquid, some answers saying solid. So we've got solid, 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 liquid, liquid. Okay, so the way to work this out. Melting point, let's think about water, for example. Okay, so water has a melting point of 0 degrees. Has a boiling point of 100 degrees. So that means at 0 degrees, water will freeze. At 100 degrees, it will boil to a gas, to steam. So taking that into account, let's think about ethanol. Ethanol has a melting point at 114 degrees. That's when it turns into a liquid. Boiling point, 78 degrees. That's when it turns into a gas. So minus 114 degrees is somewhere down here. Then we've got 0 degrees, let's say around here. If we go higher, 25 degrees is up here somewhere if we have like a scale. And then we've got 78 degrees up here. So at this point, below this point, it would be a solid. So if it's colder than minus 114, it'll be solid. If it goes past minus 114, it'll be a liquid. And then when it gets higher than 78, it becomes a gas. So at 25 degrees, it will be in the liquid phase. So the answer would be liquid. Did everyone understand that, or shall I re-explain that? Am I a teacher? No, I'm a tutor. I'm a private tutor. Okay, so we understand. That's good. So liquid. That's 1 mark. This is a 2-mark question. How can you tell? It's higher. So we can say 25 degrees C is higher than the melting point, but lower than the boiling point. Okay, everyone seems to understand. I thought that if it went below the melting point, it was a liquid. No, so melting point, if it's below the melting point, it would be a solid. So melting point of water is 0. So if we go to like -1, it would be a solid, wouldn't it? But if you have it at 1 degrees above the melting point, it will turn into a liquid. I hope that explains it. What is melting point? Melting point is the temperature at which a solid melts. So water or ice, let's talk about ice. If we get ice and then we get it to 0 degrees, it will melt into water. Boiling point is the point where it basically boils, it turns into gas. I hope that was clear. So let's move on to the next one. Look at the diagrams of sodium chloride and water. Sodium chloride has a melting point. So this is a question about melting point. What are we going to talk about for melting point? What was the things that we need to talk about? Melting or boiling point. Ionic. Yeah, so it's basically, first thing we need to figure out is this ionic, covalent, or metallic? What do you guys think? Sodium chloride. So are there any metals? Are there any non-metals? Ionic. Yeah, exactly. Reason it's ionic. Sodium is a metal. Chlorine is a non-metal. So it's ionic. Ionic compounds, they have a very high melting point, it's said there. So whenever you get a question on melting, explaining why a melting point is high or low, you need to talk about the bonds. So what can we say about the bonds? This is a 2-mark question. What can we say about the bonds then? Strong. Yeah. We always need to talk about how strong the bonds are. Exactly. So strong, use the word strong, ionic bonds. And then you always need to mention what as your second point. What would you mention? Okay, so don't get confused. It's not intermolecular force. It's not intermolecular forces. Intermolecular forces is only for simple molecular substances, not for ionic. You can talk about electrostatic forces. Ionic bonds are electrostatic forces. That's fine. So instead of saying ionic bonds, you can say strong electrostatic forces. second mark, exactly, yep, people are saying it. You need energy to break it. Energy is need, we'll say a lot of energy. You can't just say energy is needed, a lot of energy is needed to break. Okay, where do I get these papers from? It's loads of, where do I get these? I basically go online and just search them and then download them and then just get specific ones for whatever I'm going to teach. So you can get them off the website, so you can go on the AQA or OCR or edXL website and get past papers. Okay, so we got another similar question about water. Low melting point. So it's going to be the same 2 points again. You're going to talk about the bonds. You're going to talk about the energy. 2 marks again. So two points, but this time is for low. Water is H2O. So is that ionic, covalent, or metallic? Yep. So what I'm going to do is I'm going to put these videos on YouTube once I'm done with the live. So you guys can look back on it. Covalent, exactly, covalent. Now, the question is, this is where people get confused. Is it simple molecular covalent? Remember covalent, there's 2 types, simple molecular or giant covalent. Which of the 2 would it be? Simple, exactly. Simple, it's pretty much always simple, like I said, unless it's graphite, silicon, diamond, fullerenes or nanotubes. Any of these is giant. If it's not this and you know it's covalent, most likely it's going to be simple molecular. So just remember that. And what did we say about simple molecular? I think we mentioned it here in this answer. Simple molecular has weak intermolecular forces, low amount of energy to overcome the bonds. So we can give the same answer here. So it has weak intermolecular forces. Low amount of energy needed to break. How do we know the difference? So I just said it's basically, if it's graphite, diamond, silicon dioxide, or one of the fullerenes or nanotubes, it's giant covalent. If it's anything else, it's simple molecular. So I think JJ asked, how do we know the difference between simple molecular and giant covalent? How do you know the difference between intermolecular and electrostatic? So intermolecular only comes in simple molecular substances, okay? Electrostatic comes under ionic and metallic. So intermolecular, because it's got the word molecular in it, it only comes in simple molecular substances. It doesn't come under anything else. So don't use intermolecular forces for explaining any of the other ones. Only use it for simple molecular. Okay. What does intermolecular mean? Intermolecular means between molecules. Just think of like international. International means between different countries. So look at this. These are different molecules. So this is an atom. This is an atom. This is an atom. Okay. So the circles are atoms. Between the atoms, you have covalent bonds. That's one type of bond. But you also have another bond between the molecules. So between this molecule and this molecule, you have this. Let me use a thinner pen. So between the molecules, you have another bond. So the red one here is a covalent bond. The purple one is an intermolecular force. red one is a covalent bond. When you're melting these, you're not trying to break the covalent bond, you're only trying to break the intermolecular forces. These are weak, remember? Covalent bonds are strong. That's why they have weak low boiling points. Okay, so next question is on a magnesium oxide. Okay, so first of all, magnesium oxide, does that have an ionic, covalent, or metallic structure? Ionic, yeah, exactly. We know it's ionic because magnesium is a metal, oxygen is a non-metal, so it's ionic. So for ionic bonding, it's asking for a dot and cross diagram. So what we need to do is we need to draw magnesium as a dot and cross diagram. And also we need to draw oxygen as a dot and cross diagram. So they've given us the electronic structure here. It's 282. So that means the first one has 2. The second shell has 8. And the third shell has 2. Okay, this isn't the final answer, by the way. I'm trying to show you how to get to the final answer. Oxygen has 2, 6, so it's going to have 2 in the first shell. So let me draw it with with dots, because obviously it's a dot and cross diagram. Two, 6. So what the aim is here is to get a full outer shell. What's going to happen here to get a full outer shell? It's going to lose 2 electrons. Magnesium is going to lose 2 electrons. Oxygen is going to gain 2 electrons. So these 2 electrons are going to go here. Okay, so you can redraw these now. Magnesium is going to have 2 less electrons. So it's just going to be the first 2 shells. So it's going to be 2, 8 now. Oxygen is going to gain 2 electrons. 1, 2. And then the second shell, 1, 2, 3, 4, 5, 6. And then the 2 crosses are going to appear here. 1, 2, because it's just gained them. What else do we need to do then to complete this question? We have to give it its charges, and exactly, well done guys. So we need to put square brackets and the charges. This one has lost 2 electrons. It's going to have a 2 plus charge. This one's gained 2 electrons. It's going to have a 2 minus charge. And that's the answer for that one. Does anyone have any questions about this? What did the 2 brackets mean? They don't really mean anything. It's just to show that it's an ionic bond. You just put square brackets to show it's an ionic bond. They don't really mean anything. How's it got 2 plus if it's lost it? Because, I don't know if you guys remember, but electrons are negatively charged. So imagine if you were to gain an electron, you're basically gaining a negative charge, aren't you? So you're your number is going to get more negative. So if you gain 2 electrons, so this one's gained 2 electrons, you're gaining 2 negative charges. If you lose a negative charge, you do the opposite, you become more positive. So this has lost 2 negative charges, so it becomes 2 times more positive. Does that make sense? This question, I believe, is OCR, but this can get asked in any exam board, I'd say. Imagine electrons are like bad friends. If you lose 2 bad friends, it's a positive. That's a good way of saying it. That's actually a really good way of memorizing it. So well done. Okay, so on to the next one. We've got outer electrons for group 1 element potassium and in an atom of group 6. So group 1, group 6. Potassium forms an ionic compound with sulfur. So that's because one's a metal, the other one's a non-metal. So metal here, non-metal here. Describe what happens when 2 atoms of potassium react with 1 atom of sulfur. So they've told us here 2 atoms of potassium, so there should actually be another potassium here that looks the same. Give your answer in terms of electron transfer, give the formula of the ions compound. This is 5 marks, guys. It's a lot of marks. So what do you think? Where do you think you guys can get marks from this? So what are some of the things people are saying? So potassium loses electrons. Yep, you'd get a mark for that. Sulfur gains 2, you would get a mark for that. Creating a full outer shell. Yes, that won't get you a mark, unfortunately, but that's true. This is both for combined and triple science. Both potassium atoms lose 1 electron to become +1 and the sulfur will gain 2 electrons. Yes, that's good. And it becomes 2-. Okay, good, right. So I think we're starting to get it. So let's try and structure our answer to get these 5 marks. So we need 5 points here. So let's explain what's happening. We've got this electron going here, this electron going here. Okay, so that gives this 8 electrons, it makes it stable. So you get 1 mark for saying electrons are transferred. From potassium to sulfur. So next mark is to mention 2 electrons are transferred, or 2 potassium atoms lose 1 electron each. So you'd say 2 potassium atoms lose 1 electron each. That's the second mark. And then saying what each of them forms. So if potassium loses 1, it becomes K+. And then we just need to say, so that's 1 mark, that's 2 marks, 3 marks. Now for the other 2 marks, we just need to say what happens to sulfur. And I think people have been saying that. Yep, so sulfur gains 2 electrons for the 4th mark, and the 5th mark becoming S2 minus. K is left with no electrons. No, that's not true. It's this diagram only shows the outer electrons. Potassium's actually 2, 8, 8, 1. So it's actually got 4 shells, but this is only showing the outer shell. So it's technically still got 2, 8, 8 electrons in it. Okay, so everyone gets that now. Any other questions? Okay, we're doing well, guys. So on to the next one. Another covalent compound here. Sulfur can form covalent bonds. Dot and cross diagram for covalent bonds. HSH. Does anyone know what this looks like? It looks like another molecule that you need. It's one of the ones you need to memorize. Exactly, George. Water. It looks like water. Mickey Mouse. That's a good one as well. So yeah, it looks like water. H2S. Looks like H2O. Oxygen is in group 6. Sulfur is also in group 6. So this is almost identical to water. So let's do the method that we used earlier. We got sulfur, we got a hydrogen atom, we got a hydrogen atom. Let's write out how many electrons each one has on its outer shell. So sulfur is in group 6. How many electrons does it have on its outer shell? Six, good. So let's draw 6 crosses. 1, 2, 3, 4, 5, 6. We're going to add these in a second. Hydrogen, how many outer electrons does that have? Do you get a periodic table? Yes, you do absolutely get a periodic table. Would be a bit mean if they wanted you to memorize that. Yeah, 1 electron for hydrogen each. Good. So remember the plan. We want full outer shells for sulfur and for hydrogen, both of them. So let's look at hydrogen first of all. Hydrogen has 1 electron. How many does it need for a full outer shell? Needs 1, exactly. So each hydrogen needs 1. Sulfur needs how many for a full outer shell? Exactly 2. To get 8, it needs to get 8 in its outer shell. It needs 2. So hydrogen, to get its extra 1, what it's going to do, it's going to borrow 1 from sulfur. So let's say this hydrogen is this one. It's going to borrow 1 of these electrons. So let's take this cross and put it here. This hydrogen is going to borrow another 1 from sulfur. I'm going to put that in the middle as well. Then for sulfur, it's got 6 electrons. It needs 2. Where is it going to get its 2 from? It's going to get it from this hydrogen, sharing, and this hydrogen. I'm going to share that. Now we're left with 4 electrons. What do you do with the ones left over? You just add it in sulfur. You just don't put it in the shared part. Just add it in the non-shared part. And now if you check, sulfur has 1, 2, 3, 4, 5, 6, 7, 8 electrons. That's got a full outer shell. Hydrogen has 2, so that's full, and hydrogen has 2 here. Why won't the dotted electrons be on the line? Because they're being shared. We want to share them with the sulfur so that the sulfur gets 8 electrons. Okay, on to the next one. How do we know sulfur is 6? We know sulfur is 6 because it's in group 6. So what you need to do first is look at the periodic table and you'll see it in group 6. The group number tells you how many electrons there are on the outer shell. Okay, one more covalent compound here. This is oxygen, so this is actually one of the ones you need to memorize. You can work it out as well if you use my method. Let's do the same method. We've got oxygen, oxygen. We know it's in group 6, so how many electrons are there on the outer shell? Oh, yeah, so biology, guys, Mondays at 8 p.m, chemistry, Tuesdays 8 p.m, physics, Sundays at 8 p.m. So this Sunday we'll be doing electricity and physics. So you guys can join that if you want. Six electrons, exactly. So oxygen has 6. We've got 2 different oxygens here. So one's got 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6 dots. Okay, so how much does each one need? What do each of these need to get a full outer shell? 2, exactly. Both of them need 2. So let's say this oxygen is this one. It needs 2, so it's going to take 2 of the dots from the other one and borrow it. It's going to share it. This oxygen needs 2, so it's going to borrow 2 from the other oxygen, 2 of the crosses. So let's get these 2 and put it here. Everything else is left over. We still got 4 left over here, 4 left over here. Remember, anything that's left over doesn't go in the middle, it just goes around the atom. So 1, 2, 3, 4 crosses. So we've used up all of these. And then 1, 2, 3, 4 dots. We've used up all our electrons. And just to double check, make sure each one has 8. So this oxygen now has 1, 2, 3, 4, 5, 6, 7, 8 electrons. So that's okay. This one also 1, 2, 3, 4, 5, 6, 7, 8. They're both stable now. You thought they only needed 2. They do need 2. That's why 2 of the bonds go in the middle from each one. So in total, they have 4. So this is actually a double bond. For every pair that you have an extra bond. So oxygen actually has a double bond. Okay, next question. Describe the structure of a metal. It's not much you can ask about metals. What do you guys know what a metal looks like? What the structure of a metal is? Shiny, yes, shiny is a property, but the structure, when they say structure, they mean how the atoms are arranged or the particles are arranged. Conducts electricity, yes. Layers, yes. Delocalized electrons, that's what I was looking at. That's what I was looking for. Giant lattice, delocalized electrons. Yes, good. It's all up here. So I'll let you guys screenshot this at the end. All the information's here. So at the bottom, we've got metallic structure. What we've got here, strong electrostatic forces between positive ions and delocalized electrons, okay? We call it a sea of delocalized electrons. So when you talk about metallic bonding, I want you guys to remember sea of delocalized electrons. So positive ions, it's a giant lattice of positive ions surrounded by sea of delocalized electrons. positive metal ions. Okay, so back to the question. Those are the 2 points that we need to talk about. Describe the structure of a metal. So one, we say lattice, we'll say giant lattice. So you get a mark for saying giant lattice. Second mark is to say of positive ions, so the positive metal ions. Surrounded by delocalized electrons. So there we go. We've done questions on covalent bonds, we've done questions on ionic bonds and metallic bonds. So let's look at what we have at the start. So just a summary of what we've seen today. You guys can take a screenshot of this. Hope you guys can read it. If you take a screenshot, that's the summary that we have there. Hoping you can use that for your revision.